Hello, and welcome to this evening's TI Technology webinar hosted by Texas Instruments. For tonight, we're going to take a look at deciphering ratios. Are they fractions? My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. I'm really excited to introduce our two panelists, Jennifer Wilson and Michelle Reinhardt. Jennifer is in her 23rd year of teaching mathematics at Northwest Rankin High School, where she uses TI-Nspire CAS and the TI-Nspire Navigator system every day, not only to teach her students, but also to learn from them. Jennifer received the Presidential Award for Excellence in Mathematics and Science Teaching in 2011. And she also received the TQ Leadership Award in 2013. She enjoys writing mathematics curricula using technology and working with educators to incorporate good questioning techniques, engaging problems, and formative assessment in their classrooms. Thanks for being with us, Jennifer. And born and raised in rural Ontario, Canada, Michelle studied mathematics, physics, and education before moving to Texas. Michelle taught high school math and science at rural districts in Texas, while also working as a math and science consultant. Her interests include technology integration, conceptual understanding, and curriculum and instruction. She's also a mom for the second time very, very recently. So, Michelle, thanks so much for joining us tonight.
Thanks, Mike. Great to be here.
We're expecting a large crowd, so your audio is muted. Feel free to send questions to all panelists using the Q&A window on the right side of the screen. We'll also be using the chat window tonight to send general messages. We hope you don't have any audio issues tonight, but in the event that you do, try clicking Communicate in the WebEx menu, choose Audio Broadcast, and then click Join. This session is being recorded, and as a reminder, we'll provide a link to the event certificate of attendance at the conclusion of the webinar. Once that recording is available, if you'd like to follow along with your handheld or your software, and we really hope you will, we do recommend doing that with the recording. That way you can download the activities and then pause and rewind the recording as necessary. At this point, Jennifer is going to discuss our agenda.
We will be looking at several activities from TI's Building Concepts series tonight. We want to think about what is a fraction and what is a ratio and whether they are the same. We're going to build ratio tables and we'll connect ratios to graphs. We'll be sure that you know where to find these activities on the TI website, and at the end of the webinar, someone will receive a complimentary registration to the TI conference in Orlando in February.
Thanks, Jennifer. And Michelle is going to discuss our expected outcomes.
Here are three big goals for tonight's webinar. We're going to look at how we can connect ratios and proportional relationships through a coherent story across the middle school grades. Also, a big part is how we can leverage TI-Nspire technology to enhance visualization of these really critical concepts, and also how we can implement effective teaching practices to support developing these kind of challenging topics.
Thanks so much, Michelle. And Jennifer, you are good to go. As Jennifer is sharing her desktop, that chat window, which was on the right-hand side, is now underneath that green floating toolbar. And if you're going to be using the chat window tonight, if you could please send your responses to all participants as opposed to all attendees. That way, Jennifer, myself, and Michelle can see your comments. Again, that's chat to all participants. Thanks so much.
We'd like to start our discussion tonight thinking about what is a fraction. My daughter Kate noted fractions as one of the top 5 things that she learned in first grade. This was in her scrapbook at the end of first grade. She also noted that she learned how to spell big words, except apparently fractions. Fractions even made the picture for the best thing about first grade, as you can see on this slide. As a math mom, I was both excited about her declaration and concerned about her picture. Look closely at what Kate drew. So what do you say? What is a fraction? Use the chat window to tell us what you think. And as Mike noted, you can access the chat window using the bar at the top of your window. We hope that you'll figure out where that is because we have lots of interactive questions to ask you tonight. And so we hope you'll participate with us in that way. What is a fraction?
Jennifer, here are some of our first responses. A rational number. Another response is part of a whole. So we'll have some more coming in a minute as people share what is a fraction. Another person says a ratio, an explanation for a part of a whole. Another response is a comparison, part to whole, or a comparison between numbers.
All right. So there are two important aspects of fractions that provide students the opportunity to attend to precision. The first is specifying the whole. We heard a lot about that in the definitions that you just gave us as you were thinking about what is a fraction. So specifying the whole. The second is explaining what is meant by equal parts. And so if we think back to Kate's drawing here, it's unclear that Kate knows what the whole is. And it is clear that Kate does not know what we mean by equal parts when she has this picture shown for the fraction 1/3. So we're going to look at a couple of images here that come from the corrections document on fractions. Look at the top image. So we don't have to answer all these questions in the chat, but I teach by asking questions, and so it's really hard on a webinar to think about just telling. So a couple of questions just for you to think about. So what fraction is represented by the top image? If we think about that first important aspect of fractions, providing students the opportunity to attend to precision, specifying the whole is really important in this top image. What is the whole? Is the whole the two squares put together? If so, what fraction is represented by the green? Is the whole one of the squares? And if so, what fraction is represented by the image?
Some great responses coming in the chat here of could it be looked at in two ways, which really you've touched on there, Jennifer, and then different people seeing it in different ways. Perhaps it's the fraction 3/4, perhaps it's 1 1/2. So lots of great thoughts there.
All right, so specifying the whole is an important part in us thinking about what is a fraction. Look at the fractions represented, or look at the images that are on the bottom. What fraction is represented by the images on the bottom if the square is the whole? So what fractions do you see there?
Seeing a lot of 1/4 responses.
Okay, yes. So this gives us that opportunity to explain what we mean by equal parts. If we say that we have the fraction 1/4, then what do we mean by saying we have 4 equal parts and we're using one of those? So the Building Concepts TNS document gives students the opportunity to recognize what is a fraction. On the number line, the whole is the unit interval. For the fraction 1/b, here 1/2, we partition the unit interval into b equal parts, or as we see here, into 2 equal parts. One of those parts represents the fraction 1/b. So for the fraction 1/3, the fraction 1/3, we separate that unit interval into 3 equal parts. One of those parts represents 1/3. So I would like for you to answer this in the chat. How can you tell whether 1/3 or 1/5 is smaller, and why? So how can students begin to make sense of whether 1/3 or 1/5 is smaller?
So here are some responses to that. You can draw it or change it to decimal. You could look at which is closest to 0 on the number line. Another response, the denominator tells you how many times the whole was cut up.
Okay, so for that fraction, 1/b, partitioning the unit interval into b equal parts. So for that fraction 1/3, we partition the unit interval into 3 equal parts. And for the fraction 1/5, we partition the unit interval into 5 equal parts. And so we can begin thinking about the size of those parts, which one is going to be smaller. As we move to the fraction a over b, let's think about 2/3 for just a minute. So for the fraction a over b, we say that a over b is a copies of 1/b. We would say here that 2/3 is 2 copies of 1/3. 5/3 is 5 copies of 1/3. How many copies of 1/2 will be between 0 and 2 on the number line? How many copies of 1/2 are between 0 and 2 on the number line? I think I saw one quick chat that said I like thinking about fractions this way, and I really do too. I don't teach students who are first learning about fractions. I teach high school students, but when I think about the unit circle and beginning to think about 3 pi over 4 compared to pi over 4, or 2 pi over 3 compared to pi over 3, I really like that idea that 3 pi over 4 is going to be 3 copies of pi over 4. 2 pi over 3 is going to be 2 copies of pi over 3. So thinking about that as we move into a high school class with the unit circle. Let's think for a minute now about equivalent fractions. So we would say that 1/2 and 4/8 are equivalent fractions. 1/2 and 4/8 are equivalent fractions. So tell us in the chat what you think it means for 2 fractions to be equivalent. 1/2 and 4/8 are equivalent fractions. What does that mean?
Here's some responses. One is that they have the same value. Another is they have the same location on a number line. They make up the same portion of a whole. They represent the same part of the same whole.
All right, so we saw some of that in that equivalent fractions too with the images that we had here. Each one of those on the bottom, if the square is the whole, 1/4 is shown, but some of you were saying that we had 4/16 as the fraction that was shown, or 2/8 as the fraction that was shown. So let's look for just a minute at 2/3. So as we continue our work with equivalent fractions, we might ask students to determine a fraction that's equivalent to 2/3 that has 9 for its denominator. What will that be? Or we might ask them to determine a fraction equivalent to 2/3 that has 12 in its numerator. So we begin to think more and more about what equivalent fractions are and how we can begin to determine those equivalent fractions. But we'll say that 2 fractions are equivalent if they're located on at the same point on the number line. And I know that a couple of people have said that in the chat windows. So two fractions are equivalent if they're located at the same point on the number line. So we wanted to give you just a little background on the building concepts lessons before we move into the major content of our webinar tonight. So I'm going to go to the TI website. We actually have a new page for building concepts in mathematics. So I'm going to go to activities into that building concepts in mathematics page. And this will, those of you who have used some of these lessons before, this might look a little different to you. So we have here the different series. There's one on fractions, which of course we just used two of the lessons from that. And then ratios and proportional relationships, that's where we're going to spend the majority of our time tonight. We have a new series on statistics and probability, and then there is a series that's just beginning on expressions and equations. And so kind of nice thinking about all of this conceptual development and purposeful building of the progression of fractions and what is a fraction to what is a ratio and those different relationships, what different probabilities are, what is an expression, and what is an equation. So some nice work there. If we click on the ratios and proportional relationships, then you're going to see the lessons that are in that series. They are purposefully built in a progression. And you can see what the standard grade level is for these, but of course I know many teachers who have taken some of the fraction lessons that, like what is a fraction, which might start actually in grade 3, but they've used it with students who need some extra support on fractions. So while the grade level is suggested, it certainly isn't exclusive. I also know that we have used a lot of these activities in our own professional development as teachers. It's really important for our high school teachers to think about the fraction 2/3 being 2 copies of 1/3. I know that I learned about that, it's probably been 2 years now since I started learning about fractions in this way, and it really tied in nicely with one of our standards in geometry, which was on partitioning a segment into a certain ratio. And so that language was the same that we have used from fractions, and then when we think about partitioning a segment. So I think this is really important work for teachers to do as well as for students. So this is where those lessons are. If you click on a particular lesson, then you will find the resources for that lesson. You can download the zip file, which will give you all of the activity files at one time, or you can download what you need individually. Student activity in PDF or Word document form, the teacher notes, which are really extraordinary, filled with information to help us learn, and then an overview of the whole ratios, and then of course the TI-Nspire activity that goes with the TI software. It also will give you this lesson snapshot, and again, kind of just the big idea, what are the teachers doing, and what are the students doing during the lesson. So it gives you a little overview to know whether that's what you're looking for or not. All right, so we're going to go back to our software, and Michelle is going to talk with us next about what is a ratio.
Perfect. Thanks, Jennifer. So for the rest of this webinar, we're going to walk through and explore some of these different lessons from that progression that Jennifer was just showing you. And we're going to start with this activity first, what is a ratio, which is actually the first activity in the progression. So let's look at this page that we're seeing in front of us in the TNS file. And at the top of the page, we'll see the circles and squares at the top of the page are said to be in the ratio 2:3. So in a minute, Jennifer's going to click on the arrows in the lower part of the screen. And I want you to think about and then share, what do you notice? What is staying the same? What's changing? What would your students notice? So share some of your initial observations in the chat as Jennifer kind of moves us through adding some additional rows here. What are you noticing? What stays the same? What changes? What would your students notice? Okay, so we see some responses such as the shapes are maintaining the ratio, the overall shape of the rectangle is the same, each row being added is the same. We're adding 2 blue and 3 green each time. Okay, so these are some great initial observations of what we're seeing as Jennifer was moving us through there. So here's a meatier question, if you will, to ponder and then explain. Question I want to pose to you is, what does it mean to say that 2 quantities have a 2-to-3 ratio? I think we want to be back on the file for just another minute here, Jennifer, sorry.
Yeah, sorry about that.
So, that's okay. So what does it mean to say that 2 quantities have a 2-to-3 ratio? Share a possible response to that in the chat. How would you explain that? So some responses we're seeing come in that there are 2 blues for every 3 greens, 2 of one for every 3 of the other. 2 of one shape is paired with 3 of the other shape. We're seeing multiples of 2 and 3. Great. So these are some great observations and some great thoughts about what it means to say that 2 quantities have or maintain a 2-to-3 ratio. So that could be something we would look at and explore with students with this particular file and with this particular visualization. And then we might extend it with a question like this. Okay, so with that in mind, will you ever have 12 circles and 21 squares for this 2-to-3 ratio? And most importantly, why or why not? So take a minute and explain your response to that. Yes, because, no, because, why or why not is really the critical part to that. How would you explain your response? We'll give people a minute or two to ponder and then respond to that. Can you please repeat the question? Great. So the question we're kind of thinking about is, if we have a 2-to-3 ratio, will you ever have 12 circles and 21 squares for the 2-to-3 ratio kind of pictured on this page? So some responses we're seeing, you would not have the same ratio of blue to green, so this wouldn't be possible. To make 12 circles, you would need 6 groups. But 6 groups of squares would be 18, not 21. Okay? And that ties really nicely to this picture. Similar discussion of no, because 12 circles would be 6 copies of the initial pattern, while 6 copies of the squares would be 18, not 21. So some great explanations there that really making use of this visualization and the idea of copies of that initial ratio. It's an interesting question because I think it's one that we can answer the first part pretty quickly, but then articulating that why or why not really pushes our thinking a little bit further. So this file that we looked at just briefly, where we had that initial 2-to-3 ratio and then could kind of visualize some other equivalent ratios, builds a few critical ideas that really lay the groundwork for our studies of ratios and proportional reasoning. So first, ratios associate 2 or more quantities that vary together. So consider the thinking that we just did in answering the question about whether 12 circles and 21 squares, shown here, would be associated with the 2-to-3 ratio. You had to attend to these 2 different quantities, the circles and the squares, and the relationship between them. So that's one of the big ideas. And a second big idea that really comes out of this file relates to this definition of equivalent ratios and how this definition arose, if you will, from our work with this particular file. So take a minute and just kind of read through and make sense of this definition of equivalent ratios. So this definition really makes use of the multiplicative nature of equivalent ratios, and that thinking is really critical. A firm understanding of its meaning tied to a visualization of what equivalent ratios actually look like can really help students avoid common misconceptions that we'll see in later ratio and proportional reasoning studies. So let's consider the following situation. Say two of your students explained their thinking about equivalent ratios in these ways. Say that Lori says that the values in equivalent ratios are always a multiple of a common ratio, and Tomas believes that you can get equivalent ratios by adding. So consider those two potential student lines of thinking. And my question to you is, how could this TNS file be used to illustrate whether Lori or Tomas, or both maybe, are correct in their thinking? So ponder that for a minute. Ponder what Lori thinks about equivalent ratios, what Tomas thinks about equivalent ratios, and how does this TNS file illustrate one or both of those lines of thinking? Share some of your thoughts about Lori and Tomas's line of thinking here. Okay, so some great thoughts here. One great question, what does he even mean by adding? Is he adding the entire original sequence each time? That's interesting, and it kind of ties to another comment someone said about this illustration really shows or really illustrates the multiplicative nature of equivalent ratios, but multiplication is just repeated addition. So I think that's really kind of relates to one common misconception that many students hold, which is a confusion between the multiplicative change present in equivalent ratios with almost an inaccurate additive change view. So, for example, students may think that a ratio created by maybe adding the same thing to both sides, like if I add 2 to each side of a ratio, if you will, is equivalent to the initial ratio. But this file illustrates that that's not really correct. This file instead illustrates the true multiplicative nature of equivalent ratios while also demonstrating the additive relationship between equivalent ratios, where you can add different equivalent ratios to arrive at a new one. So let's kind of put some numbers to that. Consider this picture on the right, 8 to 12, if we have that ratio and we add the ratio 2 to 3 to it, we'll arrive at another equivalent ratio, namely 10 to 15. So I think y'all did a great job kind of unearthing some of the misconceptions that could come up there. What do we mean by adding ratios, and how can ratios, equivalent ratios, be both have multiplicative patterns but also have these additive patterns as well? Jennifer is now going to build on some of these ideas through another file in the progression named ratio tables.
So we've been looking at ratios in terms of that visual of the circles to the squares. Now we're just going to look at the numerical representation of those ratios. So let's look at this ratio table for just a minute. Think about what we talked about with that multiplicative relationship of ratios, the additive relationship. What do you notice in this ratio table? What do you wonder about what you see in the ratio table?
So some comments coming up in the chat include making connections to 8th grade slope, which is really interesting. We'll kind of tuck that in the back of our caps right now.
Yep.
People are noticing 2 patterns in the 2 rows. each row is going up by a multiple of the first number. Someone else mentioned that they're seeing a constant rate of change. Someone mentioned that the blue row is showing multiples of 2 or a difference of +2 between successive numbers. Someone else is saying that the recursive pattern is additive.
All right. So I'm going to move to a different page in this same document. And on this page, we have a little bit of freedom to enter the numbers of our choosing. On the previous page, we didn't have a choice about what to enter. So I want you to make some suggestions. What were your students? They have the freedom to enter a number in the yellow box. What would you enter for that value of A? What shall we try?
So maybe 4, 20. Ooh, someone wants to see 3.
Okay, I think I saw a 5.
Ooh,
so we can also enter a value for B. Any suggestions on what we might try for B?
Someone wants to see 1, yeah.
We'll try 1 in both places.
And someone wants to see 300.
Two for B. So we're actually limited on this page to entering these whole numbers or some form of those whole numbers. I think I saw pi come through there.
So Beth wants to see 0. I don't know if that's possible.
Okay. So I'll try 0 there. So 0 is not allowed. And we can also see what happens if we put 0 as the value of B.
I agree, Alyssa. That is interesting.
So when we're developing this multiplicative and additive relationship with equivalent ratios, why is it that 0 is not allowed? So we're going to move our thinking just a little bit farther. I'm going to move to the third page in this P&S document. And here too, we can put whatever we'd like in here. So I think somebody had suggested let's put 1 for the value of A, and for the value of B, I'll leave 0 in there.
Jennifer, there's also a suggestion of entering something like -12. I wonder what that would do.
Okay. So it turns out, again, on the way that this particular page is built, that we're limited to whole numbers. So the students can use this keypad. I'm actually just using my computer to type, but I can't enter a negative number.
Perfect. Good to know.
Okay, so do you see how this progression has been built with the ratio tables? We started with just 2 to 3, and as we moved through, we saw 4 to 6, and then we saw 6 to 9, and so on and so forth. And then we were able to enter numbers of our choosing, but we saw that some of those numbers gave us a whole number and some of them didn't. 0 was not allowed. And then here we are actually seeing what that non-whole number is, but 0 is still not allowed. So let's look at these two slides for just a minute. So this was from that page on which we were just working, and there are two different starting ratios, we start with the ratio 2 to 3 on the slide on the left, or the image on the left, and then 4 to 6 on the image on the right. So I want you to just look at those for just a moment. Can you see the additive nature of equivalent ratios here? Can you see the multiplicative nature of equivalent ratios? Can you think about why in the image on the right, why the fractions that are in the ratio table, why are those not reduced as we have students learning? So when I first started thinking about ratios in this manner and the additive nature that they have, which of course makes sense, as someone noted earlier, that multiplication is repeated addition, it was frightening to me to think about saying that the ratio 2 to 3 and the ratio 4 to 6, if we think about putting those together, that we're going to get the ratio 6 to 9. Will students start looking at that and thinking that that's how we add fractions? Why does that work? Why is it that we can say 2 to 3 and that ratio 4 to 6 is going to give us a 6 to 9 ratio? But really digging into the multiplicative part here and why that has to work. 4 to 6 is the same thing as 2 to 3. So thinking about that relationship and how we get 6 to 9 out of that. Now, I want us to look at these ratio tables in terms of an actual problem. So if we have the problem, if 2 pounds of fruit costs $5, how much will 7 pounds cost? I know that my nature when I see a question like this is to immediately set up a proportion and solve that proportion to find the value. But in the work that we have been doing with ratios and proportional relationships, I'm learning mathematical flexibility. I'm learning to see how to solve some of these problems in different ways, how to sometimes draw a picture to solve these problems, how to look at a ratio table to solve these problems. And so that's stretching my flexibility about mathematics, but it's also making it so that when I work with students that I have multiple ways to listen to how they solve and multiple ways to offer for those for whom one way is not enough or my way is not what they're seeing. So can you see, I'll quit talking for just a moment so you can actually look at the ratio table. How can we use the ratio table here to determine how much 7 pounds costs?
So back before you'd asked the question, a couple of people had talked about how we could use the unit rate to solve this problem. So I wonder how else we could use this actual ratio table that's shown to answer it as well.
Okay, so that unit rate that we see here, the 1 to 5 halves, we can use that and think about that multiplicative relationship. If we multiply 1 by 7 and we multiply 5 halves by 7, then we'll get to the 1250.
1750, yeah.
Answer 1750, yeah, thank you. I was thinking that is not the same thing. Okay, so what about?
Here's some other ideas coming in from chat. Someone said, well, we know that 2 plus 4 plus 1 equals 7 pounds. And so
the 2, okay, right there. So the 2 and the 4 and the 1 is going to give us 7 pounds, all right?
And so then I think the next part of that would be if those three numbers add up to the right number of pounds, you could add the costs underneath them to kind of get to your total cost. Yeah, someone just said 5 plus 10 plus 2.5, 250 is 1750.
Will give us that 1750 for that cost. So I think this is a beautiful way to make sense of how to solve a problem like this. maybe ultimately not the most efficient way to solve it when you're taking a standardized test. But I think while you're learning, making sense of how these quantities work together is really helpful. So now we're going to go back to Michelle, and we're going to think a little bit more about ratios and fractions.
Okay, so now we're going to look at a file in the progression called Ratios and Fractions. And in looking at this particular file, we're going to pull together a number of different ideas that we've already discussed this evening. So consider the situation illustrated here in front of us. Let's say that each pink rectangle on the left represents a can of pink lemonade concentrate. So we have like one can of pink lemonade concentrate right now. And each blue rectangle represents a can of water. So this first column, we see one can of pink lemonade concentrate, 2 cans of water, and that whole first column represents one batch, if you will, of pink lemonade. So as Jennifer clicks the up arrow to increase the number of sets that are shown, she is modeling making additional batches of pink lemonade. So say we make 4 batches of pink lemonade. I want us to think about in these 4 batches of pink lemonade that she has showing, what are some of the different ratios that we can talk about from this particular illustration? So what ratios are you seeing here? There's actually quite a few. Take a minute and share 1 or 2 in the chat. So some of us are seeing 4 to 8. Some of us are seeing 4 to 12, 1 to 3, 3 to 6, 8 to 4, 8 to 12, 2 to 4. Okay, wonderful. So there's all different kinds of ratios here. And really, we could talk about them in the context of the quantities. So we could talk about 4 cans of pink lemonade concentrate to 8 cans of water. So we could put all of our ratios into the context of our actual quantities. Okay, let's move forward to another page in this particular file. And on this next page, we're going to consider the same situation. So where the pink rectangles on the left represent cans of pink lemonade concentrate and the blue rectangles represent cans of water. But now on the right-hand side of the screen, we have an accompanying fraction bar illustration as well. So I want you to watch as Jennifer creates those same 4 batches of pink lemonade. And I want you to notice what changes and what stays the same as Jennifer models this process. Perfect. Jennifer, I'll have you reset that and do that one more time. And then if y'all will share some of your thoughts, what are you noticing that's changing and what's staying the same as Jennifer modeled that process of creating 4 batches of pink lemonade? Mark just said, you blew my mind. No joke, Mark. I felt the same way the first time I saw this particular file. Alyssa says that she's noticing there's still 1 pink per every 2 blue. Kelly notices that the corresponding colors equally divide. The 1 to 2 ratio is maintained. Interesting. Remember, too, that we're seeing kind of some ratios on the left and fractions on the right. And think about what you're kind of noticing there. Jamie notices that the overall numbers are the same, but the pieces are being broken into equal parts. So in the ratio depiction on the left, we may notice that the number of rectangles are increasing, but the size of our rectangles are staying the same. So like a can of pink concentrate is the same as another can of pink concentrate. But in the fraction bar illustration on the right, our pieces were actually getting smaller each time, while the unit representing the total, our fraction bar, stayed the same. So this is one way that we can illustrate kind of the complex relationship between equivalent fractions, shown on the right-hand side, and between equivalent ratios, shown on the left-hand side. Let's look at another visualization of these kind of complex ideas. So first, I want us to think about the fraction 3/2 and to quickly generate some equivalent fractions to that. So if we have 3/2, some equivalent fractions might be 6/4. I'm going to mess up on these, I'm sure. 9/6. So those are some equivalent fractions we could look at. And as y'all kind of mentioned earlier, since fractions represent a specific number, they can be plotted on a number line. So I want us to consider what some of those equivalent fractions that we just thought about, 3/2, 6/4, 9/6, what they might look like if we plotted them on the exact same number line. So let's start with our original fraction, 3/2. It would look something like this, perhaps. And then I want you to think about where would those other equivalent fractions that we just kind of generated in our minds, where would they appear in this same number line or in the same plot, okay? So let's add the equivalent fraction 6/4 to this number line. You'll see I've kind of partitioned this number line into quarters, and 6/4 ends up in the exact same location as 3/2, okay? So another equivalent fraction we had to 3/2 was maybe 9/6. So if we add that number to this number line, it also ends up at that same location. So yeah, y'all have great thoughts in the chat. They should land at the same place. They should be on top of the dot from before. Perfect. And this aligns with an important idea that Jennifer made earlier in the webinar, that two fractions are equivalent if they are located at the same point on the number line. So here we have an illustration of what equivalent fractions look like when we plot them on a number line. Okay, great. So let's consider what equivalent ratios might look like if we plotted them. First, let's generate some equivalent ratios for this situation. So say we have a situation of Tam walks 3 meters in 2 seconds. What would some equivalent ratios for that situation be? Tam goes 3 meters in 2 seconds. Jennifer, what are you thinking?
At the same rate, he would go 6 meters in 4 seconds.
Okay, sounds good. Or another one might be if you had 6 seconds, you go 9 meters in 6 seconds, something like that. Okay, those sound good. So those are some equivalent ratios, kind of using that either additive or multiplicative thinking to get there. So since, as we saw earlier, ratios associate two or more quantities that vary together, here we're talking about distance and time, we're going to need to account for these two quantities in our plot. So we won't be able to plot ratios on a number line like we did here with fractions. Instead, we're going to need a coordinate grid so that we can track both of those quantities. So here we see a coordinate grid showing distance versus time with our first ratio, 3 meters to 2 seconds, already plotted on it. So I want you to kind of pause for a second and consider where would the next equivalent ratio, maybe the one that Jennifer generated, the 6 meters in 4 seconds, where would that appear on this plot? Okay. So perfect. So here's one. Here's the location for that particular ratio, 6 meters in 4 seconds. And then I guess another equivalent ratio we had for this situation was that Tam could go 9 meters in 6 seconds. So we could plot that equivalent ratio as this particular point as well. So here we've kind of plotted 3 equivalent ratios on this coordinate plane. So my question is, what do you notice? What do you notice about the plot of equivalent ratios? So I'm seeing constant rate of change. They should appear as 3/2 x. They are linear. They form a linear relationship. These points are collinear. Great geometry term. Love that. Students would say it makes a line. Perfect. And we could talk about, that's a really special line. So people have already kind of come up with equations for that. Something interesting happens about this type of line versus maybe other linear relationships. Okay, perfect. So the next thing I want us to consider is we looked at plotting equivalent fractions, and now we've looked at plotting equivalent ratios. So we want to kind of look at these side by side because we ended up using a similar setup or numbers here in these two plots. So consider the plot of equivalent fractions on the left and the plot of equivalent ratios on the right. what do you observe about those relationships, especially as we think about this idea that fractions and ratios, while they have a lot of relationships, they are not exactly the same thing, as we see illustrated here. So what do you observe about these relationships between equivalent fractions and equivalent ratios? Great connections there, too, about how the graph on the right is showing a proportional relationship, how the graph would back up and go through the point 0, 0. Which really ties to something that Jennifer is going to touch on in the next activity. So we might want to kind of pause on this thinking, but it's something for us to come back to, thinking about the differences between equivalent fractions and equivalent ratios and how this really illustrates some of the differences between fractions and ratios. Jennifer, do you want to, I know we only have a few minutes left, but would you like to take us through a little bit of the connecting ratios to graphs, make a couple points from that activity?
Yeah, I think so. So again, this is later on in the progression of activities that connecting ratios to graphs now provides our students the opportunity to think about this ratio that's been given up here, 4 to 6, and what relationship that ratio has to what we see on the graph and what we see in the ratio table that's on the right side of the page. So these different representations that we have, and beginning to think about what other ratios we can include in the table and what might happen with those ratios on the graph as we include them. For example, what happens with the ratio 2 to 3 and where we see that on the graph, and what happens if we let the x coordinate equal 1. What happens if we let the x-coordinate equal 10? What happens if we let the x-coordinate equal 0?
And Jennifer, I'm going to jump in here for just a minute because Terry shared something in the chat. I didn't see it till just afterwards from when we were looking at that last activity with the plotting the equivalent ratios, and she said that the line will go through the origin, but 0, 0 is not an equivalent ratio. I think that's really an interesting observation she made there, and maybe it ties to what you're just showing here.
Yeah, so I think the purposefulness with which this document was built, so that we see that 0, 0 is there, it's going to be on the line, but we also have, at least for now, we have that kind of grayed out. We have the open hole there instead of the open point instead of the closed point, just to show that, so this one is not working just like all of the other points that we have on this line. So again, we're running out of time, but I want to show you just a couple of other things about this particular file. And again, this was connecting ratios to graphs. And so here we can look more closely at that additive relationship that we have between ratios. And so what will happen if I double click on this, the 2 again, and what ratio will appear in the table. And if I continue this, what will be the 6th ratio that appears in the table, or asking questions about will this ratio appear in the table versus will this ratio be on the line, some different things that we can think about there. And then as we finish up this particular activity, on page 3.2, students have the opportunity to think more about that multiplicative relationship. We can draw the line, we can enter various ratios, various values of x there, and I love this picture. What we saw on 2.2 were these congruent triangles that we have that we can ultimately move into thinking about those slope triangles. And then here we see these similar triangles and those similar slope triangles. This is one of the things that, again, we use in high school geometry, thinking about the relationship with slope triangles that are drawn on the same line when we want our high school geometry students to prove that parallel lines have the same slope. So beginning to, move them in that direction, but this definitely lays the groundwork for that. So I think that is about all we have time for tonight. We had another file that we were going to be connecting ratios to equations, where we actually do see the equations. And somebody mentioned that, I think, while Michelle was looking at some of the slides earlier, but obviously we will not have time for that. So I'm going to hand this back over to Mike. And I don't know, Michelle, if you want to say one or two more words while I do that.
Sure. Yeah, so hopefully through the activities that we had time to kind of explore and discuss tonight, and thank you all for your wonderful responses in the chat, we really wanted to kind of begin to uncover three big ideas. And those were, is a ratio the same as a fraction? And then ties into our second big idea, well, how are they different? And so hopefully you have some initial musings about that and some things you want to kind of go on and explore from that. And then really, most importantly, how can these particular building concepts files help with the visualization of these concepts and ideas? So hopefully you got some new ideas related to those big ideas throughout this webinar. Mike, I know you have some things to discuss and also a drawing for registration in Florida.
I do. Thanks, Michelle. So great segue. I would like to give away the winner of the 2 free registrations. And the winner of the 2 free registrations tonight is Mary Jane McCloskey. So Mary Jane will be in touch over email in a couple days to give you some additional information. So congratulations. And again, to everyone else, we really hope to see you in Orlando in a few months at the T-Cube International Conference, where we can look at building ratios and fractions and TI-Nspire technology, and we can connect. To receive a certificate of attendance, please click the link in the chat window. That link also listed is a link for the documents that were used tonight, so a lot of you had questions about some of the files that Michelle and Jennifer used. All of those files, including the one that we didn't have a chance to get to, is all listed in that documents link as well. If you happen to miss those 2 links or they're not working for you right now, have no fear, you'll automatically get an email in a couple days that will have a link to the recording, a link to the certificate, and also a link to the documents. If you had some questions tonight and we didn't have a chance to get them answered, please feel free to contact us with any post-webinar follow-up that you're in need of. Thanks so much, Jennifer and Michelle. I really thought I knew a lot about fractions and ratios, and you guys asked some really great questions tonight and really made me think harder than I had planned on doing about fractions and ratios. So thanks so much for all of your time and expertise.
Well, we really appreciate the participation because it just makes our learning a lot better when you engage with us, so we appreciate that very much.
Yes, thank you all for being here and being such active participants.
Thanks so much, everyone, and we really hope to see you back online next week. Have a great night.